Hi chemistry students, so we're back in module 13 and we are going to talk today about applying enthalpy to our favorite word, stoichiometry. And I decided to go cash today, so I'm wearing my alma mater sweatshirt, and I've also been hosting my in-laws, and I did not want to make a chemistry video in front of them, so they just ran out to the grocery store, and so I am making hay while the sun shines and quickly making my chemistry video. And I have not looked at the back of my hair, but we're just going to go with it and hope that it's fine and not too distracting. All right, so applying enthalpy. Remember, enthalpy is the change in energy. Applying enthalpy to stoichiometry. So to do that, we are going to look at example 13.4. Example 13.4 is on page 432. Oh, so actually this is page 432 to 437 of module 13. All right, example, no it's not. Terribly sorry, it is page 434. Example 13.4. All right, we determined previously that the delta H for the combustion of ethyl alcohol is negative 1,236 kilojoules. How much energy can be produced by burning 150 grams of ethyl alcohol in excess oxygen? Okay, so we are looking to find how much energy is produced per 150 grams, 150.0 grams of ethyl alcohol. And it said that we had already done an example with ethyl alcohol, so you wouldn't normally have to just know the chemical formula for it, but it was in the module previously, so I'll just give it to you. It is C2H6O. All right, and the things that we know. Okay, first of all, we're going to need to come up with the chemical equation. It says that we're burning ethyl alcohol. So that's a combustion reaction. So you have to remember that for a combustion reaction, you are burning the ethyl alcohol with another reactant, would be O2, and it said there was excess oxygen. So the limiting reactant is the ethyl alcohol. And then the products for a combustion reaction are CO2 and H2O. So those things you have to remember. We're also going to have to convert, whenever we're doing stoichiometry, we have to convert the grams of the ingredient to moles. Okay, of the reactant. So we're going to have to do 150.0 grams equals how many moles of C2H6O. So let's figure that out right now. To do that, we start with 150.0 grams of C2H6O. We use the factor label method, so we want grams of C2H6O on the bottom, and we are converting into moles of C2H6O. So looking at the periodic table, we would know that in 1 mole of C2H6O, we would have, I will just give it to you, 46.1 grams of C2H6O. Remember, you look at the periodic table, and the mass number for carbon is 12. For hydrogen, it's 1.01, and for oxygen, it's 16. So when you add up 2 carbons, 6 hydrogens, and 1 oxygen, that's how you figure out that there are 46.1 grams in 1 mole of it. So that's a division problem. Put it into your trusty old calculator, and you get 3.25 moles of C2H6O. So that's another thing that we know, how many moles of it we have, 3.25. And then we want to find the balanced chemical equation. So let's do that next. We know the reactants and the products. We know how many moles of it we have. We want to find the balanced chemical equation. And we also know that this reaction is exothermic because it told us in the problem that it produced negative 1,000, or that the delta H was negative 1,236 kilojoules. So remember, when it's negative, the reaction itself is losing energy and giving it off to the environment as heat. So it produces heat, it's exothermic. So we also know that this is exothermic with negative 1,236 kilojoules. All right, so that's all that we know. Now we're going to write out the balanced equation. So we have C2H6O plus our other reactant in a combustion reaction is oxygen, yields CO2 and H2O. Now remember, for combustion reactions, it's often easiest to keep this as HOH. I think that was for combustion reactions. I don't know. Oftentimes it usually is. Maybe that was for acid-base reactions. But I'll write it out like this again here too. And then we need to balance this. If you don't remember how to balance equations, look back in your books, but I think you've done enough of them by now that I think you're pretty good at them. So we would look at carbon first, and we would see that we have 2 carbons here, so 2 carbons would go here. And then oxygens, I'm just going to write it out because I don't have a lot of time to go over this. So we have ethyl alcohol plus 3 O2 yields 2 CO2 and 3 H2Os. Okay? Again, sorry, hopefully you are familiar and comfortable with balancing equations still. And then we need to add in the energy. So when it's exothermic, do we put the energy, the kilojoules, on the product side or on the reactant side? Well, remember, the reaction itself is losing the energy and producing it, giving it off to the environment. So we're going to add it to the product side as a positive. Plus, the reaction produces 1,236 kilojoules. Okay? Now looking at the equation, we can see that for every 1 mole of ethyl alcohol, we produce 1,236 kilojoules. So we want to know how much energy is produced when we have 3.25 moles of ethyl alcohol. So it becomes another factor label problem. So we start with 3.25 moles of C2H6O. We're going to multiply it by how many moles of C2H6O produce however many kilojoules. Remember, I start with the units, so I know which goes on the top and the bottom. I want the moles of C2H6O to cancel out, so that's why I have to put moles on the bottom and then kilojoules go on the top. Now I can fill in my numbers. The balanced equation told me that for every 1 mole of ethyl alcohol, so I'm going to put a 1 down here, we produced 1,236 kilojoules of energy. So that's where the number goes in there. And then we're going to multiply. 3.25 times 1,236 kilojoules equals 4,020. So the problem asked us how much energy would be produced if we burned 150 grams of ethyl alcohol with excess oxygen, and we found out that we would produce 4,020 kilojoules of energy. So that's how you apply enthalpy to stoichiometry. You have to have a balanced equation, and you have to add your energy to the product side if it's exothermic. If it would have been an endothermic reaction, we would have used energy, so we would have added it to the reactant side. Okay? So try the on your own problems in your book. on page 435, and hopefully that will continue to make sense. We're going to move on now to energy diagrams. And I will have time to share an exothermic energy diagram in this video. I'll change this back so the page numbers are correct. So we really are covering pages 434 to 437. And next up is energy diagrams, which in class we did a lab and we already looked at energy diagrams. So this is a bit of a refresher course for you. Okay, first off, you need to know what activation energy is, so I will give you that definition. Activation energy. The energy is the energy necessary to start a chemical reaction. Okay, it's the energy necessary to start or activate a chemical reaction. It is, as you'll see in a moment, the activation energy is shown as a hump, very technical term. On the graph, from the hump is from the energy of the reactants to the energy of the intermediate state. The intermediate state is just kind of like during the course of the reaction, the reaction has already begun, but it's not quite over yet. It's in the intermediate or the middle stage. So let's draw one, okay? So this is our y-axis. The y-axis shows increasing energy in kilojoules. And our x-axis just shows the rate or the progress of the reaction. So we will call this down here the reaction coordinate. So let's say that our reactants start here, and I will write underneath reactants. So this is how much energy our reactants start at. Now it has to make some sort of bump up to reach the activation energy. So that's what we call that hump. So it has to increase energy, and this is the intermediate state. Has to increase energy to get the reaction actually going, which is a good thing, because otherwise chemical reactions this paper would just all of a sudden start burning on its own, right? But no, it needs some energy given to it to get it going. So it needs this much more energy to get this particular reaction going, and I'm not giving you numbers on the side here, but of course these numbers would be increasing. Say this, sure, I'll just give you some numbers. Let's say that's 0, we'll say this is 50 kilojoules, this is 100, this is 150, okay? So it has to bump up to get the reaction going, and then let's say in this reaction, once the reaction completes, the products end with an energy back down here. So that's the energy of the products. Let's see if I have given you all that you need. Oh, and then I'm just going to draw this little arrow here. This would be the activation energy. And hopefully you can recognize that this is an exothermic. Oh, my timer is going off for me. So this is an exothermic reaction because my reactants started with this much energy, and then we ended up losing energy and giving it off to the environment as heat. So it's exothermic. All right, I got a new microwave and my timer is not stopping, so I have to go stop my timer, and I will see you in the next video.